Module 2. Interactions between drugs and the brain. Picture the human brain, a bustling metropolis of activity. Billions of cells, called neurons, chatter away in a constant dialogue, shaping our thoughts, actions, and emotions. It's a delicate balance, a harmonious dance. But what happens when an external agent, say, a psychoactive drug, joins this dance? In the grand theater of the mind, neurotransmitters are the stars. They're the chemical messengers zipping around, ensuring that every part of the brain gets the memo. Each neurotransmitter has its unique role to play. For instance, serotonin is like that comforting friend who ensures you're in the right mood, regulating hunger, sleep, and overall well-being. Dopamine, on the other hand, is the life of the party, influencing how we perceive pleasure and rewards. Then there's norepinephrine, the vigilant sentry, always on high alert, playing a crucial role in our attention and response mechanisms. But let's shake things up a bit. Introduce a psychoactive drug into this mix, and it's like adding a new dancer to our harmonious choreography. Some drugs amplify the dance steps, while others might muffle or even distort them. Take LSD as an example. This drug can introduce hallucinations, creating false messages. In essence, it's like having a dancer who's hearing a different tune and moving to its beats, leading the user to perceive things that aren't really there. In understanding these interactions, it's vital to grasp the two primary ways drugs interact with neurotransmitters. Some drugs, like Prozac, alter neurotransmitter availability. Prozac, for instance, increases the amount of serotonin in the brain. Other drugs, like opioids, directly interact with neurotransmitter receptors. They fit into these receptors much like a key fits into a lock, triggering a series of effects. Ever been puzzled by the array of names a single drug might have? You're not alone. Drugs often come with a triad of names: generic, brand, and chemical. Think of aspirin. Its generic name is, well, aspirin. But its chemical name is acetylsalicylic acid. A mouthful, isn't it? And then there are various brand names like Bayer or Anacin. It's akin to having a formal name, a nickname, and a family name. Delving deeper into the mechanics, psychoactive drugs engage with our brain cells or neurons in specific ways. At the end of each neuron is a synapse, a tiny gap across which neurotransmitters leap. Drugs can either encourage more neurotransmitters to jump across, inhibit them, or even mimic them. It's a delicate balance, and even a slight tilt can lead to profound effects, both therapeutic and harmful. Now, the human body is a marvel of homeostasis. It loves balance. When you introduce a regular dose of any substance, be it caffeine or something stronger, the body adjusts, striving to maintain its equilibrium. This adjustment leads to what we term as pharmacodynamic tolerance. It's why after a while, a regular coffee drinker might need more cups to feel the same level of alertness. And when this external substance is taken away suddenly, the body, now accustomed to its regular dose, reacts, leading to withdrawal symptoms. Let's bring this to life with Jonathan's story. Back in school, out of curiosity or peer pressure, he tried cocaine. Over time, it wasn't just a one-off experience. The occasional experimentation morphed into regular use. Fast forward a few years, and he's resorting to odd jobs or even robbery to fund his habit. What's happening here? It's not just a physical craving, but a deep-rooted psychological dependence. Cocaine has become an integral part of his mental framework. On the flip side, consider Matthew, a stalwart in the regulatory landscape of drugs. With over 2 decades of experience, he's the strategist, laying down national drug control policies, controlling budgets, and advising the highest echelons of power. He's the drug czar, an informal title for someone wielding significant influence in the world of drug regulation. Venturing further into the world of drugs in the brain, imagine you were tasked with designing a drug with an overall excitatory effect on the nervous system. Which neurotransmitter would you target? GABA, an inhibitory neurotransmitter, seems to be a good candidate. By designing a GABA antagonist, a substance that blocks or dampens a biological response to GABA, we can potentially rev up the nervous system. Lastly, in our exploration, let's join Richard, a diligent researcher in a pharmaceutical company. Eager to test a novel drug for chronic joint pain, he designs an experiment with 2 groups, one receiving the drug and another, a placebo, a substance with no therapeutic effect. To his surprise, both groups report relief. The control group, despite receiving a mere placebo, felt better. This phenomenon, known as the placebo effect, illustrates the profound influence of belief and expectation on our perception of pain. The placebo effect refers to a change in a person's symptoms that isn't attributable to the properties of the treatment they received, but rather their perception and belief in that treatment. In essence, if you believe a pill, injection, or even a procedure will help you, there's a good chance it might, even if it has no therapeutic ingredient or effect. This isn't just all in the head. The placebo effect can induce genuine physiological responses. For instance, patients given a placebo painkiller might release endorphins, the body's natural pain-relieving chemicals. Similarly, a placebo pill presented as a stimulant can increase heart rate or blood pressure. The origins of the placebo effect are still under study, but it's believed that a combination of factors plays a role. Expectation is a significant driver. When a person anticipates a pill or treatment will do something, the body responds in kind. Additionally, the conditioning of past medical experiences can influence responses. If taking a pill has previously led to pain relief, one might expect the same result again, even if the pill is now just a sugar capsule. But why is the placebo effect so crucial in research? In the quest to discern the efficacy of new treatments, researchers need to differentiate between the genuine effects of a drug and the psychological effects of simply receiving treatment. This distinction ensures that a new drug or treatment is effective beyond the power of belief. That's where placebo-controlled trials come into play. In such trials, participants are often divided into two groups. One group receives the experimental treatment, while the other gets a placebo. Neither the participants nor the researchers know who's getting the actual treatment. This brings us to the concept of double-blind experiments. A double-blind experiment is a rigorous method employed to eliminate bias. In this setup, neither the participants nor the experimenters know who is receiving a particular treatment. This blindness ensures that their beliefs or expectations don't inadvertently influence the study's outcomes. For example, if a researcher expects a drug to have particular side effects, they might unconsciously observe and report these effects more often. Similarly, if a participant knows they're receiving the real treatment, their expectations might amplify their experience of benefits or side effects. The double-blind method is especially pivotal in drug trials because the placebo effect can be potent. If participants know they're getting the real drug, they might experience improved symptoms purely based on their expectations. Conversely, if they know they're in the placebo group, they might report no change or even worsening symptoms out of disappointment. In wrapping up, it's evident that the interplay between psychoactive drugs and the human brain is a waltz of chemistry, perception, and societal influence. Every drug, every neurotransmitter, every receptor tells a story, contributing to the grand narrative of our relationship with these substances.